Achieving a H1 grade in Leaving Cert Maths is an ambitious objective, representing the pinnacle of success on the exam. It's known for being devilishly difficult to obtain, but in this video I'll show you that it might be easier than you think. I'll demonstrate and guide you through the exact knowledge required to achieve a H1 grade. Counterintuitively, the hardest and longest questions in Leaving Cert Maths often carry the fewest marks. Because of this, reaching a H1 target is more attainable than you might realise. Join me as I guide you on your mathematics education journey. Who knows, it might even get you to the pinnacle of maths excellence, that elusive H1 in Leaving Cert Maths. In the 2023 Leaving Certificate exams, the maths papers were divided into two sections. In section A, you had to answer 5 out of 6 questions, worth 30 marks each. In section B, you had to answer 3 out of 4 questions, worth 50 marks each. All in all, both sections were worth 150 marks, bringing the total to 300 marks for the paper. To achieve the H1 threshold of 90%, you would need to score at least 270 marks. After analysing the paper, I've pinpointed the easiest and most effective way to reach this target. Solving the highlighted questions would have secured a H1 grade. In this video, I'll guide you through the step-by-step solutions for each of these questions. This will demonstrate the minimum knowledge required to obtain a H1. If you can follow along and understand my explanations, then you can step into your own exam with confidence, knowing that you have the potential to achieve a H1 grade. In question 1a, the vertical bars represent the absolute value. This means that we should take the positive version of whatever number is inside. If we want the absolute value of 5 plus 3m to be 11, there's two options. Either the 5 plus 3m is equal to plus 11, or the 5 plus 3m is equal to minus 11. We can solve for m in both these cases. Let's start with 5 plus 3m is equal to plus 11. To begin, I'll subtract 5 from both sides. Then we'll simplify on the right hand side. Next, we divide both sides by 3, and then we get our answer, m is equal to 2. We can solve 5 plus 3m equals minus 11 in a similar way. We subtract 5 from both sides. We perform the calculation on the right. And then we divide both sides by 3. This gives us m is equal to minus 16 over 3. In part B, we're given an equation and asked to express k in terms of h and j. This will involve performing algebraic manipulations to the equation until we've isolated k by itself on one side. Fractions are a bit awkward, so it's a good idea to get rid of them. I'll do this in 2 steps. First, I'll multiply both sides of the equation by j plus k. Then, I'll multiply both sides of the equation by h. Since we want to isolate k, it's a good idea to group all the k terms on one side of the equation. We can do this on the right if we subtract k from both sides. Now we can factor out the common k on the right. As the final step, we divide both sides by h minus 1. This brings us to our final answer. K is equal to j over h minus 1. To solve question 2a, we can use the following fact. The derivative will be equal to 0 at a minimum point. We are given a minimum point, 3 minus 1. Importantly, the x value here is 3. Using our fact, we can conclude that the derivative, f dashed of x, must be equal to 0 when x is equal to 3. Well, this isn't much good to us unless we know what the derivative is, so we should start by differentiating. X squared differentiates to 2x, bx differentiates to b, and the constant c differentiates to 0. So we end up with f dashed of x is equal to 2x plus b. Now, we can use the fact that f dashed of x is equal to 0 when x is equal to 3. 2 times 3 is 6, so we end up with 0 is equal to 6 plus b. Subtracting 6 from both sides gives us that b is equal to minus 6. We are told that f of x has a minimum point at 3 minus 1. This implies that 3 minus 1 must be a point that's actually on the function. This tells us that f of x will be equal to minus 1 when x is equal to 3. We are told that f of x is equal to x squared plus bx plus c. We know that f of x must be minus 1 when x is equal to 3. We have a b appearing in this equation, and we've already found out what this is. It's minus 6. Now let's simplify. 3 squared is 9, and minus 6 times 3 is minus 18. We can clean up further on the right. 9 minus 18 is minus 9. From here, we add 9 to both sides, and then perform the calculation on the left to get our answer. C is equal to 8. Part B involves limits. There's 3 components in this expression, and we'll tackle each one individually. In the fraction n over n plus 1, I'm going to divide above and below the line by n. Above the line, we'll have n over n, which is 1. And below the line, n plus 1 all over n simplifies to 1 plus 1 over n. Next, let's look at the n plus 1000 over n term. We can split up this fraction by distributing the n beneath the line. This gives us n over n plus 1000 over n. We can simplify a bit here. N over n is equal to 1. Finally, let's look at the 1 over 3 to the power of n term. One of the laws of indices says that if you raise a fraction to a power, both the numerator and the denominator should get a copy of that power. So this can be rewritten as 1 to the power of n divided by 3 to the power of n. 1 to the power of n is 1, so this simplifies to 1 over 3 to the power of n. Now, we're ready to apply our limit. The key thing to keep in mind here is that if we have a fraction where the numerator is a constant and the denominator is going to infinity, then the limit will be equal to 0. This means that the 1 over n, the 1000 over n, and the 1 over 3 to the n will all go to 0 when we take the limit as n goes to infinity. 1 over 1 plus 0 simplifies to 1, so we end up with 1 plus 1 plus 0 plus 0, and this gives us 2. In part CI, we're asked to consider g of x minus 2. The effect of this minus 2 is that it decreases the y value by 2 in every location. In other words, we need to shift our function downwards by 2 units. This results in the blue curve I've drawn in here. In part 2, we're asked to consider g of x plus 3. Here, a shift of plus 3 has been applied to the input value. If we were to sub in x equal to minus 4, this would come out as g of minus 4 plus 3, which is g of minus 1. This means that x equal to minus 4 on the given function corresponds to x equal to minus 1 in g of x. In other words, there's been a shift of 3 units to the left. Applying this transformation to the rest of the points gives us the blue curve that I've drawn in. In part A, we must prove that root 2 is not a rational number. The strategy here will be to use a proof by contradiction. We'll assume for contradiction that root 2 is a rational number. Well, by definition, a rational is any number that can be written as a fraction of integers. If we assume that root 2 is rational, then it can be written as a fraction, p over q, where p and q are integers. Without loss of generality, we can assume that this fraction is in its simplest form. In other words, p and q have no common factors. If they did have common factors, then we could just simplify the fraction. So, we've assumed that we can write root 2 equal to p over q. From here, we should do some algebra. First, I'll square both sides of the equation. Then, on the right-hand side, I'll distribute the square into the fraction. Finally, I'll multiply both sides by q squared. This brings us to an equation that 2q squared is equal to p squared. Since we assumed that p and q are integers, we know that both sides of this equation are integer valued. Because of the factor of 2, we know that 2 divides into the left-hand side of the equation. Since the left-hand side is equal to the right-hand side, 2 must also divide the right-hand side of the equation. So 2 must divide p squared. This implies that p is an even number. This comes from the fact that an odd number squared returns an odd number. So if p were odd, then p squared would be odd, and we won't have 2 dividing p squared. So the only option is that p is even. Now, since p is even, it must have a factor of 2. This means that p squared will have 2 factors of 2. In other words, it must be divisible by 2 times 2 is equal to 4. So we figured out that the right-hand side, p squared, is divisible by 4. Since the left-hand side is equal to the right-hand side, the left-hand side must also be divisible by 4. In other words, we know that 4 divides 2q squared. Eliminating a factor of 2 tells us that 2 must divide q squared, and this implies that q is even. This is using a similar argument to above. If q was odd, then q squared would be odd, and we wouldn't have 2 dividing q squared. Well, we've shown that p is even, and we've shown that q is even. This means that they have a common factor of 2. But earlier, we assumed that p and q had no common factors. So we've obtained a contradiction, and this concludes our proof. In part B, we must solve an equation involving logs. There's an interesting pattern in the numbers in the bases. We have 3, 9, 27, and 81. These are all powers of 3. 9 is 3 squared, 27 is 3 cubed, and 81 is 3 to the power of 4. It'll be sensible to convert all these logs into base 3. We can do this using the formula in the hint. Applying this statement with a equal to 9, b equal to t, and c equal to 3 tells us that log base 9 of t is equal to log base 3 of t divided by log base 3 of 9. The denominator here can be typed into our calculator. When we do this, it returns a value of 2. We can do a similar thing to deal with the log base 27 of t and the log base 81 of t. Log base 27 of t will be equal to log base 3 of t divided by log base 3 of 27. Using our calculator, the denominator here evaluates to 3. Now, for the log base 81 of t, this can be written as log base 3 of t divided by log base 3 of 81. This time, the denominator evaluates to 4. We've now written each of our logs in terms of log base 3. Let's go back to the original equation and write in what we found. Now, we can factor out a common factor of log base 3 of t on the left-hand side. Next, let's divide both sides by 1 plus a half plus a third plus a quarter. Performing the calculation on the right tells us that log base 3 of t is equal to 4.8. To find the value of t, we need to get rid of the log base 3. The opposite of log base 3 is power base 3, so here we should raise both sides as a power base 3. This gives us that t is equal to 3 to the power of 4.8. To answer C part I, we must explain what log base 6 of m means. Well, log base 6 of m is the power which 6 must be raised to if you want to obtain an answer of m. Another way to think of this is that it's the value of x which satisfies the equation 6 to the x is equal to m. In other words, it's the mystery number which must be put in the power of the 6 to get out an answer of m. In the next part of the question, we're told that m is a real number which is greater than 6. we must think about log base 6 of m. Well, if you were to put a 1 in the power of a 6, you would get 6 to the 1, which is 6. We can deduce that a number less than 1 in the power will give you a value which is less than 6. A value which is greater than 1 in the power will give you a value which is greater than 6. Since we're told that m is greater than 6, the number in the power will need to be greater than 1. From here, we can conclude that log base 6 of m must be greater than 1. In part A, we must differentiate the function f of x is equal to 1 over 5x squared plus 7. This expression is a fraction. The quotient rule can be used to differentiate fractions. This states that u over v differentiates to v du dx minus u dv dx, all divided by v squared. Here, u refers to the number above the line. In our situation, u is equal to 1. V is the expression below the line. We'll have v equal to 5x squared plus 7. To apply the quotient rule, we'll need to differentiate both of these expressions. The constant 1 will simply differentiate to 0, so du dx is equal to 0. To differentiate 5x squared, we use the rule of multiplying down by the power, then reducing the power by 1. So 5x squared differentiates to 10x. The plus 7 is a constant, and this will differentiate to 0. So dv dx is equal to 10x. From here, we simply have to sub in these expressions into the quotient rule. To finish, we can simplify the numerator. Anything by 0 gives you 0, and minus 1 times 10x is minus 10x. In part C, we're given 3 sets, A, B, and C. F is a function which maps from A to B, and G is a function which maps from B to C. The first task is to find the value of g of f of 3. To begin, we should find f of 3. Well, 3 appears here. When we apply f, we get mapped to the icon of the world. When we apply g to this icon, we end up at w. So g of f of 3 is equal to g of the icon of the world, which is w. In part 2, we must explain why g is injective but not surjective. Well, by definition, a function is not injective if 2 inputs map to the same output. Another way to think of this is that it is injective if no output value has more than one arrow coming into it. If we look at the output values, x, w, y, and z, none of these have more than one arrow coming in. So this means that g is injective. A function is surjective if every single output value has an arrow coming into it. This means that it's not surjective if we can find an output value with no arrow. Well, looking at the output set C, we see that y has no arrow coming into it. So the function g is not surjective. In part A, we're presented with 2 functions, f of x and g of x. The first task is to find two values of x for which these functions are equal. Our starting point is the equation f of x is equal to g of x. Well, f of x is x plus 4 and g of x is x squared minus 2, so let's write these in. Now, I'll group everything on the right hand side by subtracting x and subtracting 4 from both sides. We can simplify on the right. Minus 2 minus 4 is equal to minus 6. We now have a quadratic expression on the right hand side. This can be factorised. To do this, we need to pick a pair of numbers which multiply to minus 6 and add to minus 1. Here, minus 3 and plus 2 do the job. So our factorisation is x minus 3 times x plus 2. We know that these two factors must multiply together to give 0. The only way that this can happen is if one of the factors is 0 itself. So either x minus 3 is equal to 0 or x plus 2 is equal to 0. Both of these cases are straightforward to solve. If x minus 3 is 0, we can add 3 to both sides to get x is equal to 3. If x plus 2 was equal to 0, we can subtract 2 from both sides to get x is equal to minus 2. In part 2, we must find the area between the two functions in the range x is minus 1 to x is plus 2. An important thing to observe here is that f is always greater than g in the specified range. This means that we can find the area by calculating a definite integral of f of x minus g of x. The limits will be the specified x values, minus 1 and 2. Well, by definition, f of x is equal to x plus 4 and g of x is equal to x squared minus 2. Now, distributing the minus sign gives us minus x squared and minus minus 2, which is plus 2. Next, we can combine the constant terms. Plus 4 plus 2 is 6. We're now ready to integrate. A useful thing to remember here is the rule for integrating powers of x. Raise the power by 1 and then divide by the new power. Looking at the x, we can think of this as x to the 1. This will integrate to x squared over 2. Minus x squared will integrate to minus x cubed over 3. A constant term will always integrate to that constant times x. So 6 integrates to 6x. We needed to calculate the definite integral from minus 1 to 2. To calculate this, we sub in the upper limit, x equal to 2, and sub in the lower limit, x equal to minus 1, and subtract away the answers. From here, all we have to do is some calculator work. When we sub in the upper limit, it comes out as 34 over 3. When we sub in the lower limit, it comes out as minus 31 over 6. To obtain our final answer, we simply need to calculate 34 over 3 minus 31 over 6. This comes out as 33 over 2 square units. In question 7, we are given a function v of t which specifies Fiona's speed t minutes after passing a specific point A on a motorway. In part A, we need to find out Fiona's speed when she passes the point A. Well, t represents the time in minutes after passing the point A. At the instant she passes A, 0 minutes will have passed. So all we need to do is sub in t equal to 0 into our function. When we do this, we get out an answer of 109 kilometers per hour. In part B, we must work out Fiona's acceleration 5 minutes after passing the point A. Acceleration can be thought of as the rate of change of your speed. Differentiating a function allows us to find the rate of change. This means that the acceleration is found by differentiating the speed function that we were given. To differentiate 2 over 3t cubed, we can use the rule for differentiating powers. Multiply down by the power and then reduce the power by 1. This gives us 2t squared. The same rule can be applied for the minus 6t squared. We multiply down by the power, then reduce the power by 1. This gives us minus 12t. A constant times t simply differentiates to the constant, so 13t will differentiate to 13. Additive constants differentiate to 0, so the plus 109 will differentiate to 0 and simply disappear. This means that the acceleration function, v dashed of t, is equal to 2t squared minus 12t plus 13. We want to find the acceleration 5 minutes after passing the point A. So we should sub in t equal to 5 into the acceleration function. When we perform the resulting calculation, we end up with an answer of 3 kilometers per hour per minute. In part C, we must find the time at which Fiona reaches her maximum speed during the first 4 minutes. Well, there's an important fact in differentiation which says that minimum and maximum points occur when the derivative is equal to 0. So if we want a maximum of the speed function v of t, we should set the derivative v dashed of t equal to 0. Thankfully, we found this function in part B. V dash of t was equal to 2t squared minus 12t plus 13. We end up with a quadratic equation. This can be solved using the quadratic formula. T will be equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Here, a refers to the number in front of the t squared, so a is 2. B is the number in front of the t, so b will be minus 12. And c is the constant by itself, so c will be plus 13. Let's sub these values into our formula. From here we can simplify. Minus 12 is plus 12. The expression under the square root evaluates to 40. And beneath the line we have 2 times 2, which is equal to 4. To deal with the plus minus sign, we need to split into 2 cases. In the first, we replace this symbol with a plus, and in the second, we replace it with a minus. Both of these fractions can be evaluated using our calculator. In the first case, we end up with 4.58, and in the second case, we end up with 1.42. So these are the two time values where the derivative v dashed of t is equal to 0. We were asked for a time that occurred during the first 4 minutes. This rules out the 4.58, so we're left with a final answer of t equal to 1.42. If you wanted, you could prove that this was indeed a maximum point by showing that the second derivative is negative at this value. v double dashed of t comes out as 4t minus 12. When you sub 1.42 into this function, you end up with minus 6.32. In part D, we must use integration to work out Fiona's average speed over the first 5 minutes. To find this, we'll calculate the definite integral from 0 to 5 of the speed function v of t. Then we'll divide this by the length of the interval. In other words, we'll multiply it by 1 over 5 minus 0. 5 minus 0 is equal to 5, and we can write in the expression for v of t from the previous page. Now it's time to integrate. The main rule we'll apply here is for integrating powers. Raise the power by 1, then divide by the new power. Focusing on the 2 over 3 t to the power of 3, we'll raise the power from 3 to 4 and then divide by 4. This gives us 2 over 12 times t to the 4. For the minus 6t squared, we raise the power from 2 to 3 and then divide by 3. So we end up with minus 6t cubed over 3. 13t is the same as 13t to the power of 1. So to integrate this, we'll raise the power from 1 to 2 and then divide by 2. This gives us 13t squared over 2. A constant will integrate to that constant times t. So 109 integrates to 109t. We wanted the definite integral between 0 and 5. To find this, we need to sub in the upper limit, 5, and sub in the lower limit, 0, and subtract away the answers. When we perform the calculator work, the upper limit evaluates to 561.6667. The lower limit evaluates to 0. When we multiply this by the 1 over 5 in front of the brackets, we end up with 112.3333. The question wants us to round to 2 decimal places, so our final answer is 12.33 kilometers per hour. In part E, we are provided with some information. V dashed of 1 is greater than 0, and V double dashed of 1 is less than 0. We are presented with 4 graphs, and we must determine which of these V of t must look like. The derivative V dashed represents the rate of change of V. Since V dashed of 1 is greater than 0, this means that we have a positive rate of change. In other words, V of t is increasing at t equal to 1. Since graphs A and C are decreasing at t equal to 1, we can rule these out. The second derivative, V double dashed, represents the rate of change of V dashed. Since V double dashed of 1 is less than 0, this means that the rate of change, V dashed of t, is decreasing. In other words, the rate of ascent is getting smaller. The function is increasing, but it's starting to level out. B is the only graph with this property, so our final answer here is graph B. In part F, we're told that there's 2 points on the motorway, A and B, which are 10 kilometers apart. We need to find the minimum time in minutes that a driver could get from A to B while never driving above 100 kilometers per hour. Well, the larger the speed is, the shorter the journey will take. So if we want to minimize the time, it makes sense to maximize the speed. Our speed is never allowed to go above 100 kilometers per hour. However, we can travel at exactly 100 kilometers per hour for the duration of the journey. To find our time, we can use the distance, speed, time triangle. Since we want to find the time, we should block out this portion of the triangle and look at the two quantities which remain. Here we have distance over speed. We're travelling between point A and point B, and the distance between these is 10 kilometers. Our speed is 100 kilometers per hour. So we end up with 10 over 100, which is 0.1. Since the speed was in kilometers per hour, the unit here is hours. However, the question wants the answer in minutes. To convert from hours to minutes, we simply multiply by 60. This brings us to our final answer of 6 minutes. In question 9, we must investigate the factors of different numbers. The first task is to list the 5 different factors of 2 to the power of 4. Well, using our calculator, 2 to the power of 4 is equal to 16. The factors will be the numbers which divide evenly into 16. With a little bit of thought, we can list these out. The factors are 1, 2, 4, 8 and 16. There's a very nice pattern here when you write these factors as a power base 2. 1 is 2 to the power of 0, 2 is 2 to the power of 1, 4 is 2 to the power of 2, 8 is 2 to the power of 3, and 16 is 2 to the power of 4. So, to find all the factors of 2 to the power of 4, all we have to do is write all the numbers from 0 to 4 in the power of a 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. This pattern is very helpful when it comes to part 2 of the question. Here, we need to work out how many factors 3 to the 7 has. Here, all we have to do is write all the numbers from 0 to 7 in the power of a 3. The factors are 3 to the 0, 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4, 3 to the 5, 3 to the 6, and 3 to the 7. There's 8 numbers on this list, so 3 to the 7 has 8 factors. In part 3, we must work out how many factors 2 to the 10 times 3 to the 12 has. To solve this, we'll need to generalize the idea from above. The factors of 2 to the 10 can all be written in the form 2 to the a, where a is a whole number between 0 and 10. the factors of 3 to the 12 can all be written in the form 3 to the b, where b is a whole number between 0 and 12. To find the number of factors for 2 to the 10 times 3 to the 12, we'll have to consider all the different combinations of these. In other words, the factors will be of the form 2 to the a times 3 to the b. For example, 2 to the 4 times 3 to the 2, 2 to the 7 times 3 to the 0, or 2 to the 1 times 3 to the 9. So there's 3 examples, but there's many, many more. To find the total number of factors, we'll have to figure out how many there are. Well, a, the number that's in the power of the 2, must be a whole number between 0 and 10. So there's 11 choices for a. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. b, the number in the power of the 3, must be a whole number between 0 and 12. There's 13 choices here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. To find the total number of ways to pair a choice with A with a choice for B, we should multiply together the 11 by the 13. This gives us our final answer of 143 ways to form a factor of 2 to the 10 times 3 to the 12. In part B, we're looking at pairs of factors of 12. In other words, that's pairs of natural numbers, x and y, such that x multiplied by y gives you 12. The first task is to complete a table showing these pairs. The key to doing this is the following. Whatever numbers we write in, each column must multiply together to give you 12. This means that if we have a column with one number written in, the other number must be 12 divided by that number. The y value in the first column will be 12 divided by 1, which is 12. The y value in the second column will be 12 divided by 2, which is 6. The y value in the second last column will be 12 divided by 6, which is 2. And the x value in the final column will be 12 divided by 1, which is 12. There was one column in the middle which had neither box filled in. Each of the rows should contain all the factors of 12. If you look through the x row, you'll notice that 4 is the missing factor, so that's what we should write in. To find the corresponding y value, we divide 12 by 4 and get 3. In the next part of the question, we must plot these 6 points on a coordinate diagram. The first point has an x value of 1 and a y value of 12. So we go to 1 on the x-axis, 12 on the y-axis, and plot a point at their intersection. The next point has an x value of 2 and a y value of 6. The next point, 3, 4, is already plotted for us. After this, we've an x value of 4 and a y value of 3. Next is an x of 6 and a y of 2. And finally, we have an x of 12 and a y of 1. This gives us 6 points plotted on the diagram. In part 3, we're told that the relationship between x and y is that y is equal to 12 over x. We need to draw the graph of this function above. Well, we've already drawn in 6 reference points. To draw the graph, all we have to do is join these points with a nice smooth curve. In part C, we are told that a tangent to the curve y equals 12 over x is drawn at the point p, 12 over p. We must show that the equation of the tangent line is equal to a given expression. If we look through the formula book, we'll find a result for the equation of a line. Y minus y1 is equal to m times x minus x1. To use this formula, we need to know 2 things: a point on the line and the slope of the line. We are given the point directly. It's p 12 over p. This gives us the x1 and the y1 values for the formula. Finding the slope m is a bit more tricky. To do this, we'll use the fact that the derivative dy dx represents the slope. It'll be a good idea to find what this derivative is. The function is y equal to 12 over x. We can think of this as 12 over x to the power of 1, and then use the law of indices, which says we can move a power from below the line to above the line as long as we change the sign. This gives us 12x to the minus 1. We can find the derivative dy dx by differentiating this expression. We'll want to use our rule for differentiating powers of x. Multiply down by the power, then reduce the power by 1. Here, the power is minus 1, so we multiply down by minus 1, and then we reduce it from minus 1 to minus 2. This gives us minus 12 x to the minus 2. Using our laws of indices, this can be rewritten as minus 12 over x to the plus 2. We want to find the slope at the point p 12 over p. The x value here is p, so to find our slope, we should sub in x equal to p into our derivative. This gives us minus 12 over p squared. We're now ready to sub in to the equation of a line formula. x1 is equal to p, y1 is equal to 12 over p, and m is equal to minus 12 over p squared. In the target expression we were given, y is all by itself on the left-hand side of the equation. We should do some algebra to get our equation into this form. To start, let's multiply out the brackets on the right. Minus 12 over p squared times x gives us minus 12 over p squared x. Minus 12 over p squared times minus p gives us minus 12p over p squared. The two minus signs here combine to give us a plus, and we can cancel the p above the line with one of the p's below the line. Now, we can remove the minus 12 over p from the left-hand side by adding 12p to both sides. If we want to add together fractions with the same denominators, we simply add the numerators. So 12 over p plus 12 over p comes out as 24 over p. As our final answer, we end up with y equal to minus 12 over p squared times x plus 24 over p. This is precisely the expression we were asked to obtain. In question 10, we're presented with a triangle. It has a base of 2 and a perpendicular height of 8. We are provided the first 3 terms of a sequence based on this triangle. The first term contains 1 rectangle. The second term contains 2 rectangles which are of equal height. The third term contains 3 rectangles of equal height. In part A, we must draw the fourth pattern. Well, the fourth pattern will contain 4 rectangles of equal height. The triangle has a perpendicular height of 8 units. If we split this evenly across 4 rectangles, then each one will have a height of 2 units. To draw the pattern, we should start by drawing horizontal lines through the triangle. We start by drawing a line along the base. Then we move up 2 units and draw a line. From here, we move up another 2 units and draw a line. And finally, we move another 2 units and draw a line. These 4 lines represent the bottom side of each of the 4 rectangles. To finish the pattern, we simply need to draw in the other 3 sides of each rectangle. In part B, we must show that the total area of the 3 rectangles in T3 is 32 over 3 square units. To tackle this question, we should try to find the area of each rectangle individually. To do this, we should try to find the height and the width of each rectangle. The total height of the triangle is 8 units. Since this is split equally among the 3 rectangles, each rectangle will have a height of 8 over 3 units. At the bottom of the triangle, we have a width of 2. At the top of the triangle, we simply have a point. So here, the width is 0. So essentially, the width grows from 0 units at the top of the triangle up to 2 units at the base. Since the sides of the triangle are straight lines, as we move down from top to bottom, the width will be increasing at a steady rate. The total increase in width is 2 units, and this happens over the duration of 3 rectangles. This means that the growth per rectangle will be 2 over 3 units. We can illustrate this in our diagram. At the top of the triangle, we have a width of 0. When we reach the bottom of the first rectangle, this will have grown by 2 over 3. By the time we reach the bottom of the second rectangle, the width will grow by another 2 over 3. This gives us a width of 4 over 3. By the time we reach the base of the third triangle, the width will again increase by 2 over 3. So here, the width is 4 over 3 plus 2 over 3, which is 2. Now that we know the heights and widths of each rectangle, we can find their areas by multiplying them together. The area of the top rectangle will be 8 over 3 times 2 over 3. This comes out as 16 over 9. The area of the middle rectangle will be 8 over 3 times 4 over 3, and this comes out as 32 over 9. The area of the bottom triangle will be 8 over 3 times 2. This comes out as 16/3. To find the total area of the three rectangles, all we have to do is add these three results together. This gives us an answer of 32/3 square units. This is precisely the answer that we wanted to obtain. In part D, we're told that the total area of a different sequence of rectangles is AN is equal to 8 times n minus 1 over n. We must find the first value of n for which AN is greater than 95% of the area of the triangle. Well, there's a formula which says the area of a triangle is a half times the base times the perpendicular height. Our triangle has a base of 2 and a perpendicular height of 8. So the area is a half times 2 times 8, which comes out as 8 square units. 95% of this area would be 8 times 95%, which is 7.6. We want to have AN greater than 95% of the area, which means that we'll need AN greater than 7.6. When we write in the given expression for AN, we end up with the following inequality. 8 times n minus 1 over n is greater than 7.6. We can solve this inequality to find the value of n. To begin, I'll multiply both sides by n. Then, I'll multiply out the brackets on the left. 8 times n is 8n, and 8 times minus 1 is minus 8. Next, I'll group the n terms on the left-hand side by subtracting 7.6n from both sides. We can simplify on the left. 8n minus 7.6n is 0.4n. From here, we can remove the multiplication of 0.4 by dividing both sides by 0.4. After we perform the calculation on the right, we end up with n is greater than 20. Since n is a whole number, the smallest value of n which satisfies this would be n equal to 21. And that's our final answer. In part E, we're presented with two diagrams. In diagram A, we have a square-based pyramid. The side length of the square in the base is c. The perpendicular height of the pyramid is h. In diagram B, we have the same pyramid, but this time we have a horizontal slice taken x units from the top. We're given a formula to find the area of the shaded section. S of x is equal to x squared c squared over h squared. In part I, we are given an expression for the volume of the pyramid and then asked to find this volume. The expression we're given is the definite integral from 0 to h of s of x dx. Well, we're told what s of x is. It's x squared c squared over h squared. So let's write this in. Because of the presence of the dx, we are integrating with respect to x. This means that c and h can both be treated like constants. Multiplicative constants can be brought outside the integral sign, so we can bring out the c squared over h squared. Now we can integrate. The rule for integrating powers of x is to raise the power by 1 and then divide by the new power. We have x to the power of 2, so we raise the power from 2 to 3 and then divide by 3. Since we had the definite integral from 0 to h, we should sub in the upper limit, x equal to h, and sub in the lower limit, x equal to 0, and subtract away the two answers. 0 cubed over 3 simply comes out as 0, so the expression inside the square brackets simplifies to h cubed over 3. H cubed divided by h squared is h, so we end up with a final answer of c squared h over 3 units cubed. In part 2, we are told that x starts to increase at a rate of 3 units per second. This increase will cause s of x to increase as well. We must find the rate of change of s of x with respect to time at the instant when x is half the perpendicular height of the pyramid. This is a related rates question, and there's 3 quantities of interest here: x, s of x, and t, the time in seconds. We are asked to find ds dt, the rate of change of s of x with respect to the time t. The first line in the question tells us that dx dt, the rate of change of x with respect to t, will be 3. On the previous page, we were given an expression for s of x. It's equal to x squared c squared divided by h squared. This can be rewritten as c squared over h squared times x squared. If we differentiate this expression, we can find the rate of change ds dx. C squared over h squared is a constant. When we differentiate, this will simply remain on the side. To differentiate the x squared, we multiply down by the power, then reduce the power by 1. This gives us 2x. Combining this into a single fraction gives us 2xc squared over h squared. So, we need to find ds dt. If we multiply above and below the line by dx, we can rephrase this in terms of the two derivatives we just found. ds dt is equal to ds dx times dx dt. We found that ds dx is equal to 2xc squared over h squared. And we found that dx dt is equal to 3. Since 2 times 3 is 6, we end up with 6xc squared divided by h squared. We need to consider the instant when x is half the perpendicular height of the pyramid. Well, h represents the perpendicular height, so half of this would be h over 2. So we'll want to take our derivative and sub in x is equal to h over 2. 6 divided by 2 is 3, and the h above the line will cancel with one of the h's below the line. This brings us to a final answer of 3c squared over h square units per second.